special families of homogeneous metrics on homogeneous spaces. Some of these metrics are very, very important by some reason, very different reason from point of view of geometry or analysis and so on. But we will see that there are some not so popular, but also very important classes of metrics on some special, maybe not so special, but on some more or less general homogeneous spaces. And I try to explain why some classes are important, or why some classes is more important than another. Okay. Okay. In what follows, we suppose that the Riemannian metric G of Riemannian homogeneous space is generated with the inner product of this form. Hence, we will use the identification of metric and this inner product. And if not said otherwise, the manifold is considered to be connected. Okay. Now, let's recall that we discuss what is the reductive decomposition and reductive complements for Lie algebra G, isotropic subalgebra H, which are corresponding to homogeneous space G mod H. Yes, I recall that reductive complements should not be unique, but sometimes, of course, it's unique. And let's fix some reductive decomposition, or by another words, this complement P, and consider the following definition. The G-natural reductive space is a space such that the corresponding inner product has this property. Look at this formula, please. Here, x, y, z are any tangent vectors to the tangent space at a given point, or in our assumption, x, y, z, any vectors from reductive complement P. If we consider more closely this formula, we see that it means that at x, adjoint x is skew symmetric operator with respect to a given inner product or given Riemannian metric. Yes. Sometimes we can obtain such metrics just as a restriction to P of some at G invariant or bi-invariant, in other terms, positive definite inner product on Lie algebra G. If is the case, then we call such a metric, or such inner product if you want, then we call such metrics G normal homogeneous. If we consider the this property at G invariance in the term of Lie algebra, it means exactly the following: all at H, all adjoint operator of any element of Lie algebra G is skew-symmetric. It's very easy to check. Hence, at G invariance matrix on the Lie group, it's one of the important example of such matrix with this property. And hence we have a lot, a big amounts of such examples. Really, any compact Lie group G could be supplied with some at G invariant matrix. Therefore, we have some Riemannian structure, Riemannian matrix with this property, at least one. Hence, after this, we can produce another matrix with this property, taking some homogeneous spaces with the same Lie group of isometry and with some isotropy subgroup H, and project and we consider also the corresponding matrix, which could be produced as projection of a fixed edge invariant metric on the Lie group. Hence, we have many examples of metrics with this property. This property is very helpful in many computation, which are related to the computation of some curvature characteristic and so on and so on and so on. It's a very big simplification for such computation to have this property. Hence, we have the most important thing, the most important property in what I said. It's these metrics are very good for computations, at least. Okay, now let's consider some other definition. Yes, another variant to consider this class of homogeneous Riemannian manifold, normal homogeneous Riemannian spaces, is the following. We take for a given Riemannian manifold, we consider some isometry group G in this case, and with stabilizer or with the isotropy subgroup H at a given point X. And if there is a bi-invariant, non-degenerate Riemannian, respectively semi-Riemannian metric tensor on G, such the natural projection P from this group manifolds to this homogeneous space with a given metric, such this projection is Riemannian or semi-Riemannian submersion. Here we can consider the more formal way to say what does it mean, Riemannian submersion. In some cases, it could reformulate as submetry. We will discuss it a little later. This property submetry is a little better because it could be formulated just in metric terms without differential and so on and so on and so on. And I will explain this. I'll try to explain this a little later. Okay, some natural projection from group with bi-invariant matrix to a given homogeneous space. If this projection is submersion, then we have normal homogeneous space. In the case, this metric is Riemannian. And if this metric is semi-Riemannian, but this is Riemannian, of course, then we have a natural reductive homogeneous metric. It's just another way to define this matrix. Okay. Now, the classification of naturally reductive homogeneous space of dimension not greater than 5 was obtained by Kowalski and Hecke in 1985. And new ideas for this classification in other dimensions was suggested by Agricola, Ferreira, and Friedrich a little much more later. This allowed to get classification of naturally reductive homogeneous spaces in dimension 6. And in the very recent paper by René Storm, we can find a new approach was developed, and the which was developed for classification of naturally reductive homogeneous spaces in dimensions 7 and 8. Hence, we have classification up to dimension 8 just now. And we recall some property of Killing vector field of constant length, because such vector fields are related to some special metrics on Riemannian manifolds. Okay, it's possible to find some more or less interesting surveys on these topics. We recall only some more or less important for us properties. Okay, for example, this lemma. Let X be a Killing vector field on a Riemannian manifold. We don't think that this Riemannian manifold, we don't suppose that this Riemannian manifold has a special property, not necessarily homogeneous, for example. Then the following conditions are equivalent. 3 conditions. The first one, X has constant length on this manifold, which is assumed connected, of course. A covariant derivative of X with respect to X is 0 on this manifold. And very important, the third one, every integral curve of the field X is a geodesic in Riemannian manifold, in the given Riemannian manifold. These 3 properties very important, and this condition are equivalent. Now, one more lemma. If a Killing vector field X from Lie algebra of Killing vector fields has constant length on our manifold, then for any other Killing vector fields Y and Z, we have the equalities, this one and this one. This equalities holds at every point of manifolds. If G acts on manifold transitively, then condition 6 implies that X has constant length. Moreover, the condition 7 also implies that X has constant length, but if we assume that M is compact and G is transitive on M. Hence, we have more or less simple conditions to check, is this Killing vector field of constant length or not? Okay. There is a proof very easy. You can check it maybe later if you want. I'll skip this because it's very easy. There is some machinery. Now, the following lemma. For Killing vector field X, Y, Z on a Riemannian manifold, we have this quality. What we have this. Here we see the covariant derivative of vector field Y with respect to vector field X. And from the another side, we have more or less simple thing, only brackets and inner products. Hence, we have a way, we have a method to compute the covariant derivative of one Killing vector field with respect to another one. It's quite easy, but of course, we should note that covariant derivative of one vector field, or one Killing vector field with respect to another one, should not be Killing vector field. Not necessary. But in any case, we can compute it in any point if Lie algebra of Killing vector field are transitive on a given manifold. Then we easily find this vector field by this formula. Okay. In particular, if we have this property, that means that inner product between x and y is constant on a manifold, then this covariance derivative is very easy, this one. It also could be helpful in some special computations. Yes. Another very important, very helpful lemma. If X be Killing vector field and Y is Killing vector field of constant length on a Riemannian manifold, then we have this formula for Riemannian tensor R. And this formula is also very helpful in various computations with some special homogeneous manifold. The proof is very easy. I will skip it. And one more, maybe not so obvious, but in any case, we recall that we have identification of elements of Lie algebra of Killing vector fields with elements of Lie algebra of isometry group of these Riemannian manifolds. And if we have this identification, then we can consider this property. If x, y are some Killing vector fields such that the inner product between x and y is constant on manifold, then for every inner automorphism of Lie algebra G, we get this formula also at every point of M. Hence, we can replace x and y by ax and ay. And in any case, we will have the this formula which is held on manifold. In particular, if x vector field x has constant length, then A of x has the same property for any inner automorphism of Lie algebra of Killing vector fields. That's very simple fact, but it's very helpful also. This is a proof, very formal and in fact very easy. I also prefer skip it. Let's consider the example, the following. The following simple observation gives many examples of Killing vector fields of constant length on homogeneous Riemannian manifold. Okay, suppose that a Lie algebra G of Killing vector fields is transitive on Riemannian manifold, and the Killing vector field Z commutes with this Lie algebra. In particular, that could be in the center of this Lie algebra. Then this vector field has a constant length on this Riemannian manifold. Why? The proof is could be right in one line. Really, for any vector field X from Lie algebra of Killing vector fields, we have the following. If we differentiate this inner product with respect to this vector field, Then we have, of course, 0, because this is a constant. Therefore, we have this property. Yes. Since Lie algebra of Killing vector field is transitive on M, then we have another inclusion, another implication. From this one, from this formula, we get this. Why? If Z is commute with X, then this bracket is 0 always. Therefore, this is 0. But we know that this is a derivative of this value with respect to vector field X. Therefore, derivative with any Killing vector field of this value is 0. Since Lie algebra G is transitive, then in every direction, the derivative is 0. Therefore, this is a constant. It's very easy. And this simple observation gives many examples of Killing vector fields of constant length. Okay. Hope it's easy to understand. Now, what about classification of Killing vector field of constant length? In fact, it's not. It is not a good idea to classify such Killing vector field on all remaining manifolds, because we can modify the remaining structure very easy, and it's not serious result because it's impossible to classify in some sense. But if we consider some special Riemannian manifold, for example, Riemannian homogeneous spaces, then the problem is non-trivial and reasonable. To classify for a given homogeneous Riemannian space, classify all Killing vector field of constant length. More exactly, we can assume that this is a full isometry group, for example. Therefore, we use with all Killing vector fields that it's very helpful from some point of view. But more general setup, if we consider some isometry, a group of transitive group of isometry of on a given homogeneous spaces, and consider only Killing vector field from corresponding Lie algebra. It's more complicated problem. But in any case, this setup, two variants of setups, are very reasonable. But the problem is not so easy, in fact. Okay, it's reasonable to assume that G is compact and simple at first. And we have some partial classification. For example, Ming-Su and Joseph Wolf obtained classification of normal homogeneous Riemannian spaces that admits non-trivial Killing vector field of constant length. They consider the case when G is compact and simple, and some intermediate subgroup H. And result of classification is very strange. Every of these spaces are locally symmetric, or its universal remaining cover is either odd dimensional sphere of constant curvature over remaining symmetric spaces over remaining symmetric space SU to N mod SPN. It's one simple family of symmetric space. Therefore, the results would be tell us that such spaces are quite rare, not so easy to find, in fact, non-trivial remaining homogeneous space with non-trivial Killing vector field of constant length. And if we have such Killing vector field, then this homogeneous Riemannian manifold should have very special property. In fact, very, very special property. In some sense, it's very similar to locally symmetric, and so on and so on and so on. It's an informal way to understand this result, yes. But in any case, this result is very important in the context of study of general remaining homogeneous manifold. But in fact, we have no serious result in this direction now. But it should be quite interesting. This result with normal remaining homogeneous space, but not for only Riemannian, but pseudo-Riemannian, was considered in the next paper by Sue Wolf. You can see it in references. There are some structure results on Lie algebra of transitive isometry group on a general compact homogeneous manifold with non-trivial vector field of constant length. There are some restriction on structure of such Lie algebra, but we will discuss only some of them. Now, some very special isometry which are related to Killing vector field of constant length. We should note that there exists a connection between Killing vector field of constant length and so-called Clifford-Wolff translation or Clifford-Wolff isometries in a Riemannian manifold. What is the definition of this translation? Okay, recall that a Clifford-Wolff translation in a Riemannian manifold is the isometry S moving all points in this manifold one and the same distance. Hence, we have this formula for inner or length metric generated by a Riemannian metric tensor. Yes, all points move the same distance. Of course, it's easy to consider natural examples. For example, Euclidean space, Euclidean plane, and vector translation, any parallel translation to a given vector have this property, of course, but not necessarily this. There are some natural isometry with this property on odd dimensional round sphere. From this isometry was found by Clifford, I think, and therefore we have this terms, Clifford translation. Sometimes it's used term Clifford translation, sometimes Clifford-Wolff, but Wolff used such kind of isometries in his investigation of homogeneous spaces, and therefore this variant of terms is more reasonable to my mind, for example, and we will use this one, Clifford-Wolff translation. Such translation are studied in various papers and so on and so on. So not only for Riemannian case, but also for pseudo-Riemannian, for Finsler case, and of course it can be studied for any metric space because the definition is very easy, pure metrical. Yes. For example, now we have the series result on finite homogeneous metric spaces, which obtained jointly with Professor Berestovsky, but it's another story. Example. The following observation gives many examples of Clifford-Wolff translation, homogeneous Riemannian manifolds, just as in previous example for hidden vector field of constant length. Suppose that the Lie group G act transitorily on a given Riemannian manifold Mg by isometries, and some isometry F commutes with this transitive group G. Then F is a Clifford-Wolff translation. Why? This is a very short proof. Indeed, for any point xy in M, we can choose the element A from G, such move x to y. Yes, yes, because transitive action. Now, for inner matrix, we have the following. The matrix between x and f at x is the same as between a of x and a of f of x, because A is isometry. Now we can change A and F, interchange these two isometries because F commutes with all G and with A in particular. Now we have that A of x is just y, and this is f of y. Hence, one line proof shows that this isometry move all points one of the same distance. Therefore, we have natural example of Clifford-Wolff translation. Very easy example. But it's quite general situation in many cases. Now, another example with the same idea. Let K be a compact subgroup of Lie group J. J is also compact. Oh, not necessary, but we can think this compact. Then consider H diagonal embedding K in the product group J times K. This is formal definition. Yes. It's easy to see that even one multiple G act transitively on the homogeneous space M G times K mod H. It's really very easy that G is a transitive group of isometry of this manifold. But let's consider on K in this product, we see that K commutes with J because of definition of product, direct product. Hence, K consists of Clifford-Wolff translation on the manifold M for every G times K invariant Riemannian matrix, just by the previous example. Hence, we have very serious, how to say, very serious amount of Clifford-Wolff translation on these Riemannian manifolds with any invariant matrix. We have so many Clifford-Wolff translation as element in the group K. So it's not so obvious, but it's fact. Now, some problems. by some reason I could not go to the next page. Oh, unpredictable, really.
Could you try the up and down arrows next to the number of slides?
Just a moment. I tried various ways.
Your trap, stop sharing and share again.
Just a moment. I try. Oof. Did you see my slides? No?
Yes.
No. Very strange.
You have to stop sharing.
Yes, I'll stop.
Close your PDF, reopen it.
Oh, okay, close the PDF. Okay, I'll try. What's the reason? Do you know?
Computer, your computer.
Yes, it's a simple idea. Okay, I'll try. Did you see anything?
Yeah.
And let's check. Oh, good. Good. Yes. Sorry. Do you hear me?
Yes.
Maybe you can close again.
But try,
One more time? Okay.
No, it's actually okay. I can see you.
Open the next page and start from the next page.
but if you try these
Oh,
arrows,
yes,
yeah,
good. Yeah.
one next to the number, these are fine.
Very strange. Okay, sorry. Okay, another example with the same idea. And we consider some special type of homogeneous space, Legere-Bata space. Let's F be connected compact simply group, and K is a natural number. Consider so-called Legere-Bata space, F to the power K mod diagonal embedded F. For K equal to, we get a reducible symmetric space, of course. For K3 and more, we get some generalized symmetric spaces for some definitions. But what about metric property? We can supply it with any invariant remaining metric G, sorry. The not unique possibility, of course. And the structure of invariant matrix on this homogeneous space is quite complicated. It could be considered in special paper. It's very complicated, in fact. It should be noted that for any compact Lie group F, Algebra space Fk mod diagonal F is diffeomorphic to the Lie group F to the power chi minus 1. It's also not so difficult to see. And the most important for our discussion, it's easy to see that every copy F in this Fk consists of Clifford-Wolff translation on a given algebra space, as well as very copy of the algebra F chaotic in this sum, direct sum, consists of Killing vector field of constant length for any invariant Riemannian matrix G. Why is this the case? If we remove some copy F in this product, then all other F constitute a Lie group of this type, which acts transitively on algebra space. Hence, any elements of this F commute with some transitive isometry group. And we have the same idea to prove that any element of any copy F consists of just Clifford-Wolff translations. It's very easy to check and very not easy to understand without this idea, but it's fact, it's very easy. And I repeat, it's the fact for any invariant Riemannian matrix on this homogeneous space. Now, let's go to the next topic. Yes, let's consider some Killing vector field Z. And this vector field, by natural way, generate a one-parameter isometric group gamma of T on Riemannian manifolds. Yes. And let's consider the following property. This element of generated one-parameter isometric group are Clifford-Wolff translation. Sometimes this is the case. If we have this property, then the vector field Z should have constant length. It's very easy to check. In fact, in one line of computations, and or even without computations. And more interesting that this assertion can be partially inverted. If a Riemannian manifold has the injectivity radius bounded from below by some positive constant, it is a case, for example, for every compact manifold or for every homogeneous manifold, and Z is Killing vector field of constant length on this Riemannian manifold, then the isometries gamma of T from the one-parameter isometric group generated by this vector field are, in fact, Clifford-Wolff translation, at least for sufficiently small absolute value T. Hence, we have some relation between Killing vector field for constant length and one parameter Clifford-Wolff isometry groups. It's very important because we can translate some problem for Clifford-Wolff translation to the language of Lie algebra, a Killing vector field of constant length, and back. And sometimes it's possible, it's helpful to use one side a reverse idea or direct idea. Okay, and natural definition of Clifford-Wall homogeneous space. Any metric space M rho is a Clifford-Wall homogeneous if for any points x, y in M there exists an isometry F, Clifford-Wall translation of the space such that it moves x to y. Okay, it's very easy. For any 2 points, we have some Clifford-Wall translation that move 1 point to another one. This very serious restriction on the metric structure of metric space, of course. And obviously, every such metric space are homogeneous, of course. Therefore, Clifford-Wall homogeneous is some more serious properties than simply homogeneous. Moreover, yes, and definition for Riemannian manifold. Riemannian manifold is Clifford-Wall homogeneous if it is Clifford-Wall homogeneous with respect to its inner metric, rho g. It's natural. And in addition, it's G Clifford-Wall homogeneous if we can take isometries from this subgroup G of full isometry group of Riemannian manifolds. It's also very natural definition. And I repeat that there are some very natural examples. For example, Euclidean spaces are Clifford-Wall homogeneous. It's very easy to check. We know it's from school. And all odd dimensional round spheres are also Clifford-Wall homogeneous. It's in fact resulted by Clifford. And also all Lie groups with bi-invariant Riemannian matrix also has this property. Why? Because left shift commute with all right shifts, and right shifts are act transitively. Therefore, all left shifts are Clifford-Wall translation, as well as all right shifts are Clifford-Wall translations. Therefore, any Lie group with bi-invariant Riemannian matrix has this property. It's Clifford-Wall homogeneous. And of course, direct metric product of any number, any quantity of Clifford-Wall homogeneous Riemannian spaces are also Clifford-Wall homogeneous. It's very easy to understand. And the most important thing in this topic is that we have some opposite statements. This results which obtained together with Professor Berestowski. A simply connected Riemannian manifold is Clifford-Wall homogeneous if and only if it is a direct metric product of an Euclidean space, odd dimensional spheres of constant curvature, and simply connected compact simple Lie groups supplied with bi-invariant Riemannian matrix. That's a full classification. Therefore, this property is very, very strong. Very, very strong. Yes, and we should also note that every geodesics in Clifford-Wall homogeneous Riemannian manifold is integral curve of suitable Killing vector field of constant length. It's also a very serious restriction. Yeah, it's very easy to see. Therefore, this property very restrictive, but in any case, quite interesting. Now, some other very important types of homogeneous spaces. A Riemannian manifold is symmetric if for any its point x there is isometry F such f of gamma t is gamma of minus t for all arc length parameterized geodesics. Gamma of t with gamma of 0 is x. Therefore, this isometry reversed every geodesics at this point, and this very well known Riemannian manifold symmetric spaces are studied, classified by Cartan. Of course, all such manifolds are homogeneous, and for suitable reductive decomposition, we have G is H plus P with this property. The bracket of P and P is in H. It's true for symmetric space or locally symmetric space. And in some sense, it's very simple case, very simple subclass of Riemannian homogeneous space from exactly because of this property, for example, because of this property. Now, a little more general class, a weakly symmetric. A manifold is weakly symmetric if for any geodesic gamma of t, there exists an isometry f such we have f of gamma t is gamma of minus t for all t. Now we consider only one geodesic, and for this geodesic, we can take spatial isometry, not one and the same isometry for all geodesics, but spatial isometry for a given geodesics. If J is a full isometry group and H is isotropy subgroup at a point X, then for suitable reductive decomposition, G is H plus P, this property is equivalent to the following one. For every Z from P, there exists A from isotropic group H, such that at A of Z is minus Z. It's the same as this relation. Yes. If we have these properties, then we have a weakly symmetric space. Or weakly symmetric spaces also homogeneous. Yes. Now, some history. The class of weakly symmetric spaces introduced by Selberg. The above definition is equivalent also to the following one. A homogeneous Riemannian manifold M G mod H G is a weakly symmetric space if any 2 points PQ from M can be interchanged by an isometry A from G. It's the same. This property does not depend on the particular invariant matrix G. It's algebraic property, not geometric realized. Weakly symmetric spaces M G mod H have many interesting properties and are closely related with spherical spaces, commutative spaces, Gelfand pairs, etc. See the Book of Wolf, yes, and the dissertation of Yakimova, and some other articles and books. Yes, and another important class of homogeneous space is isotropy irreducible. If a homogeneous space G mod H with compact H is such that the group at H acts irreducibly on the reductive complement P from a reductive decomposition, this space is called isotropy irreducible. Yes, at H acts irreducible on P. It admits exactly one up to homotopy G invariant Riemannian matrix, because all H invariant matrices are different by a multiple, in fact. Therefore, we have, in fact, only one invariance metric up to homotopy. And this G invariant matrix should be Einstein, because Ricci form is also should be proportional to the Riemannian metric. By the same reason, we have isotropy reducible space. If even the group at H0 act reducible, H0 is connected component of the unit in H, act reducible on P, then the space is called strongly isotropy reducible. Strongly means that the connected component of unit act reducible. These spaces are classified with the works of Wolf, Manter, Ziller, and Wang, and we can find many excellent surveys and books about this. Note that all non-compact isotropy reducible spaces, non-compact isotropy reducible spaces are symmetric, and all compact isotropy reducible spaces are normal homogeneous, because we have only one metric, in fact, for any isotropy reducible space. Yes. And now let's discuss most strange thing as the class, a remarkable class of compact homogeneous spaces, and now known as the generalized Wöhler spaces. Generalized Wöhler spaces. These spaces were studied from the point of view of section curvature. Einstein met with the Ricci flow in special geodesic by various authors. And what's about definition? Yes. Consider homogeneous almost effective compact space G mod H with the compact semisimple connected liquid G and its closed subgroup H. And let's this one be a minus scaling form on the Lie algebra G, and consider the orthogonal complements P of H and G with respect to this form, minus scaling form. Let's suppose that G mod H is such that at H invariant module P is decomposed as a direct sum of three at H invariant irreducible submodules, pairwise orthogonals with respect to a given matrix. Hence, we have this decomposition P into the sum of P1, P2, P3. All two of these submodules are orthogonal with respect to these inner products, and every of these P1, P2, P3 are at H invariant and irreducible. Another property, we demand that the bracket of Pi is in H for any I, 1, 2, 3. This condition resembles the condition of local symmetry for homogeneous spaces. Yes, P bracket P is in H. Therefore, such spaces are also called three locally symmetric spaces by this reason. And now we will use the term generalized Wöhler spaces. Why? Because we have three very important spaces of this kind, which was introduced by Wöhler. This is, in fact, they are manifold of complete flux, the complex fermionic and Cayley projective planes. This is a formal definition, but it's not so important now. These spaces are interesting because they admit invariant Riemannian metrics of positive sectional curvature, as it was proved by Wöhler in his very well-known paper. Therefore, the term generalized Wöhler homogeneous, it's natural, I think. Generalized Woloch spaces. Now, another example of such manifold is simply group SU2. In this case, we have trivial isotropy subgroup. And another example of generalized Woloch spaces are Kähler-C spaces of this form. And there are more three-parameter family of generalized Woloch spaces of this kind: SO n1 and plus n2 and 3 mod SO n1 times SO n2 times SO n3, and the same for symplectic groups. That's natural examples with this property. Why this class of homogeneous space are important? Because they are quite simple, but not so simple as symmetric spaces. Therefore, you can use it to check some properties, some property of Riemannian quantities, for example, yes, for sectional curvature, Ricci curvature, some other properties, and check some hypotheses, some conjectures, and so on and so on and so on, because it's possible to do for this class of spaces. It's possible to use some computer algebra for these classes, because it's quite easy. Not very easy, but quite easy. Hence, it's important as a model spaces for check some conjectures, for example. Yes, some properties of the generalized Woloch spaces. This inclusion implies that H plus pi py is a subalgebra of G for any y. Therefore, we have three subalgebra T1, T2, T3, and the pair Ty H is irreducible symmetric. It could be non-effective, of course, but not so important. We easily get from the definition that the bracket of P, J, and Pk is in Pi exactly, in the another model, in the third model, for pairwise distinct indices. Yes, and we have also this this formula. Therefore,
You're right, I don't understand, sorry.
yes.
Above it's written Pi and Pj is an H. Now you write Pi, Pj is an Pk.
Sorry, I don't understand your questions. What's the problem?
The first blue formula,
This
Pi,
one?
Pj, yes, is an H.
Yes.
And then another blue formula,
This one?
yes.
Yes. This is corollary of this one. Why not?
They're distinct, I, J, K, and J.
Yes, they are distinct. If we take K is equal to J.
Sorry, yes, yeah.
Yes. Okay. It's the same property, in fact. This one and this one. Okay. This is a distinct A, I, J, and K. And all this pair G, T, I are also reducible symmetric. Therefore, we construct generalized Woloch spaces with using several pairs of symmetric spaces. Yes. Therefore, the structure of this generalized Woloch space is not so complicated. A little more about these spaces. Denote by di the dimension of the corresponding submodels py, and consider an orthonormal basis in py with respect to a given, with respect to chosen inner product, and consider this expression defined by the equality, this one. We take brackets between two basic vectors in p alpha and p beta, and multiply by basic vectors in p gamma, and take square of this this inner product. And we take it for all triple alpha, beta, gamma. These symbols I, j, k are symmetric in all three indices by invariance of the matrix. And moreover, the spaces under consideration, we have this value is 0 if two indices coincide. Therefore, we have in fact one important quantity, a big A, which is corresponding to triple 1, 2, 3. Yes, one important numerical characteristics. And it's very easy to check that the dimensional dy is greater than 2a, and the equality could and the equality is equivalent to this implication. This means that h commute with pi, and moreover, a is 0 if and only if the space G mod H is locally a direct product of three compact irreducible symmetric spaces. It's very trivial example of generalized Woloch spaces. Therefore, interesting cases when this characteristic is not 0. Now we can consider this quality A1, A2, A3, which is A big divided by D1, D2, D3. This number is real number between 0 and 1/2, and therefore we have triple A1, A2, A3 in this cube, in three-dimensional Euclidean space, in this cube, and every generalized Woloch space we can represent as a point, more generally speaking, as a point up to interchange of this value. Of course, we can change A1 and A2, for example, and A1 and A3. But in any case, it's triple of points, yes. And therefore, we have some interpretation of set or generalized Woloch spaces as some points in three-dimensional cube. It's give a possibility to classify and consider some property of this special Riemannian homogeneous manifold, and so on and so on and so on. You can find some interesting result in papers in the references. I also recall that in some papers with my co-authors, we studied a normalized Ricci flow on these generalized Woloch spaces. There are some interesting results. And we use some special technique. We developed some special technique for this class of homogeneous spaces. And we also study evolution of positively curved metrics on the Woloch spaces, 3 Woloch spaces. It's also quite interesting, and there are some unexpected results in some cases. But all these show only one. These spaces are quite good to use it for check some special Riemannian or generally speaking geometric properties. Therefore, we should take in mind that there are some very, very important and very helpful, very useful class of homogeneous space, generalized Woloch spaces. There are several papers devoted to Einstein metrics on generalized Woloch spaces. We have almost classification, almost complete classification on these spaces, but it's very interesting that on every such space there is at least one Einstein metric up to homogeneity, but no more than 4 Einstein metric. And it's very interesting to consider the evolution of number of this Einstein metric, which we consider some close in some reasonable sense of each to other generalized Woloch spaces. Now I should also add that in papers by Ronte-Jurgis and Souris, they studied geodesics of some special kind in generalized Woloch spaces. And in fact, all standards problem of geometry are studied in the case of generalized Woloch spaces, almost all, I think. And if you have some special property which you should check, for example, for homogeneous Riemannian spaces, then you should start with this class. I think it should be very useful and helpful to check it at first for this class of homogeneous spaces. And now it's the final slide for this lecture, because the next is geodesic orbit spaces. Yes, I'm finished.
Thank you very much for a very nice lecture.
Thank you.